digit expansions, or more precisely about an algorithm for optimal joint expansion with odd digits. And this is based on my joint work with Professor Clemens Heuberger. For the start, I will tell you something about digit expansions. How are they, for example, used in cryptography? Then I will give you a short insight into construction principles of our algorithm. And finally, I will tell you how we show optimality of the given algorithm and how complex the algorithm is. So for the start, how does it go here? Sorry. No. Sorry. Okay, it should work now. Okay, so for the start, let us see what digit expansions are and joint digit expansions. Yesterday, in first presentation, we had a definition, and the colleague from Ukraine had a definition. But here I will give you an example we are all familiar with, and this is binary expansion. So if we consider integer 13, then the standard binary expansion is 1101, and we write it always from right to left. So it means that the least significant digit is on the right. And this is a digit expansion if we have one integer, and a joint digit expansion is if we have more than one integer. So for example, if we have a pair of integers, then a joint digit expansion is a matrix where each row is expansion of respective integer. And generally for any arbitrary digit expansion, we have dimension of expansion. Here in first example, the dimension is 1, and in the second one, it's 2. Then we have the radix or the basis. In case of binary expansion, this is 2, but of course, basis can also be some other. Then we have the digit set. So here we have the digits 0 and 1. Then we have the length of the expansion. So for one-dimensional digit expansion, this is just the number of digits. And in case of joint digit expansions, this is the number of the columns of the matrix. And finally, what we have is a Hamming weight or joint Hamming weight. So in one-dimensional case, this is number of non-zeros. So here we have 3. And in case of a matrix, this is not the number of non-zeros, but the number of non-zero columns. So in this case, we have again joint Hamming weight of 3 because we have only 1 0 column. And now I will show you how can this be used in cryptography. For example, in cryptography over elliptic curves, here we have 2 sketches of the same curve. And the left sketch gives us visualization of point addition. So if we have points P and Q, 2 distinct points, and Q is not inverse of P, then if we draw a line which connects these 2 points, then this line will also intersect elliptic curve in one more point. We reflect this point on the x-axis, and we get P plus Q. So this is point R. And the second, on the right sketch, we have a visualization of the operation doubling. So if we have a point P, then we draw a tangent line in this point, and this tangent line intersects elliptic curve in one more point. We reflect it on the x-axis, and we get point Q, which is 2P. And altogether, these 2 operations yield so-called double and add method. And now let us see how can we combine double and add method and digit expansions. So for example, if we would like to calculate a multiple of a point, we have a point and we would like to calculate 13P, then we could calculate P plus P plus P plus P, but it is better to take a digit expansion. So here we take binary and we go from left to right. And so the first digit is 1, so we add P. Then the next digit is 1, but we double this, what we had, and we add P. Then we double what we had, we add 0, and we double what we had, and we add P, and altogether we came to 13P. And the next step is the calculation of linear combinations. So if we would like to calculate a linear combination, then we could with the method from above, calculate 13p, for example, and 5q, and then just add them. Or we can use Strauss algorithm, which is also sometimes called fast-Shanner's method. And it is based on the fact that we can pre-compute point p plus q. So for this purpose, we take our joint digit expansion, and we go again from left to right. So the first column is 1, 0. This means add 1p and 0q, so we add p. Then we double what we had, and q we have 1, 1. This means 1p and 1q, so we add p plus q. Then we double it, and we don't have to add anything because this is a 0 column. And then we double it, and we add p plus q. And altogether, we have calculated 13p plus 5q. So how many operations are needed? We need, if we use basis 2 and binary expansion, or generally any expansion, the doublings corresponds to the length of the expansion. And the number of additions is then the Hamming weight or the joint Hamming weight of the expansion. And of course, next question is it possible to reduce this number of operations? Because if we can calculate these linear combinations even more efficiently, we could use even larger parameters, and this is, of course, good for any crypto system. So the number of doublings we cannot reduce, because this is just how binary expansions work, or expansions with basis 2. So we concentrate on reduction of number of additions. And this means the reduction of the joint Hamming weight of the expansion. And such reductions lead to so-called low-weight digit expansions. So the goal is to reduce joint Hamming weight, or in other words, to increase number of 0 columns, because when we have a 0 column, we do not have to make addition. And how can this be done? So if we use radix 2 and our digits 0 and 1, then the representations are unique. So we cannot increase number of 0 columns. So we have to introduce some other digits in the digit set. And since in elliptic curves, the point subtraction is computationally as expensive as point addition, this means that we can introduce negative digits. So we introduce negative digits in our digit set. For example, digit we have 0, 0, 1, and we can introduce -1. However, this leads to redundant number systems, because when we have one positive and one negative digit in a digit set, we can represent any integer. So every integer has infinitely many possible representations. And this means that the goal is to detect of all these possible expansions which one are minimal, and then of course to give algorithms which compute minimal weight joint expansions. So I have already mentioned the digit set 0 plus -1. Here we have 3 existing algorithms. We have joint sparse form, which gave Solinas in 2001 for pairs of integers. So he introduced basically this idea in his work. Then a generalization to arbitrary dimensions was first given in 2003 by Pros. And then another generalization, which is called simple joint sparse form, was given in 2004 by Grabner, Heuberger, and Prodinger. And when we consider some other digit sets with odd digits.
Sorry, can you motivate again the negative digits? Why does it make sense?
Because in elliptic curve, a point subtraction is computationally as expensive as point addition. Should I say it again? Should I? Because you can see it, for example, here. So, okay, this. So, because we have here point R, and subtraction is basically addition of inverse, and inverse is just reflection on the x-axis. So it's just one, it's computationally same expensive. Okay. So sorry. And thank you for your question. Okay, so we have 3 existing algorithms for these digit sets. And if we consider other digit sets with odd digits, but I repeat with odd digits, and of course digit 0, then in this case we have only some approximation algorithms. And this means that they have a certain offset to minimal weight. And how do we know that there exists an offset to minimal weight? This is because with some other techniques, it is possible to compute for a digit set what a minimal weight an algorithm should have without giving algorithm per se. And so this means for us that we have already information about pre-computed minimal average weights. And this brings us to our research area. So we are interested in giving those algorithms. So with odd digits and of course digit 0. Okay, now we learned something about digit expansions and how can they be used in cryptography. And now I will tell you about something more about our algorithm. So what we managed to do is to give algorithm for pairs of integers and for the digit set 0, plus, minus 1, and plus, minus 3. So this is the general setup of the algorithm. We plug in 2 integers as a vector and our digit set. And result is a matrix with minimal weight joint expansion, which is written from right to left. So the first column, the least significant column is on the right. It has index 0. And then we do what? We select digits from our digit set. After we select them, we compute integer minus digit sets divided by 2 because we use radix 2. And we go to the next column. We increase our index and we do it until our input vector is just a 0 vector. And within this setting, it is, of course, the biggest challenge in selecting the digits in a way that we really get minimal weight expansions. But prior to selecting these digits, I will tell you some other observations regarding the algorithm. So first, let us take a look at output. If we consider integers 5 and 7, then we can get 3, with our given digit set, we can get 3 different expansions. And this 3 dash is minus 3 and 1 dash is minus 1. And all these expansions have minimal weight 2, because we always have 2 non-zero columns. And with a given digit set, we cannot make expansion with weight 1. So this means that this is a minimal weight expansion. So that is why we have imposed some syntactic constraints. And this is self-inflicted. This is, of course, not necessary to do, but we were motivated with joint sparse forms. So we introduced so-called shape condition for pairs of integers. And I will explain it. There are 3 properties I will explain on this example. So this is output of the algorithm for integers 73 and 47. So the first property is that of any 3 consecutive columns, at least 1 is a 0 column. So here we can see that really any 3 columns, 1 is a 0 column. Then a column with 2 odd digits is followed by a 0 column. So here we have a column with 2 odd digits, 1 and minus 1, and it is followed by a 0 column. And here we have also 2 odd digits, 3 and 3, and basically they are followed by infinitely many 0 columns. We just don't write them. And then we have a third property, which is a property regarding adjacent odd digits. So basically, we avoid having adjacent odd digits in one row, and we can maximally have 2 adjacent odd digits, like here, and only in this one specific situation. So when the right column has 1 odd digit and 1 0 digit, this can also be vice versa, and the left column has 2 odd digits. But again, this was self-inflicted. So, and if we go through these properties and take a look at our three possible expansions, we will notice that the first one does not satisfy condition that the column with two odd digits is followed by a zero column. So we eliminate this. But the other two expansions, they do fulfill shape condition. So this tells us that this is that our shape condition is unfortunately not uniquely determined. But this is, yeah, unfortunately. Okay, so then just few observations regarding the digit set. So what can we do with our digits? If I have as an input an even integer, then I have to choose even digit, and my only even digit is digit 0. But if I have an odd integer, I have to select an odd digit. So for example, if we take a look at integer 27, then I can choose digit 3, and this gives me, if I choose it, this gives me 27 minus 3, this gives me 24. If I choose digit 1, this gives me 26. If I choose digit minus 1, this gives me 28. And if I choose digit minus 3, this gives me 30. Or what we can see is that we get 4 consecutive even numbers. And of any 4 consecutive even numbers, one of them will surely be congruent 0 modulo 8, one will be congruent 2 modulo 8, one will be congruent 4 modulo 8, and one will be congruent 6 modulo 8. Or we can also reformulate this statement. And we can say that our digit set contains a unique representative for all odd residue classes modulo 8. And I have highlighted unique representative because this is important property of this digit set. So this is not a general property that all representatives are unique, but in case of this digit set, it is. Okay, and based on these simple observations, we define some functions. And the two most important functions are so-called h function and setting function. So what we plug into this function is our integer, our digit set, and wanted congruence modulo 8. This is what we plug in. Then the first formula calculates us the digit. So if I say, okay, I want it to be congruent 0 modulo 8, which is very often the case, because if I choose 0 modulo 8, I will for sure have two zeros. Okay, then the algorithm will say, okay, this is digit 3. Then the so-called setting function calculates integer minus selected digit, which may seem now maybe as overkill. Why do we calculate this? But in some cases, if we use congruent 0 modulo 8, we have to take a closer look at two-adic valuation of this setting, because integer, which is congruent 0 modulo 8, can also be congruent 0 modulo 64. And this is important information about how many zeros we will get. Okay, and then based on this, sometimes we have to take a look at successors and so on. And altogether, we built our algorithm based on some case studies. So there are 3 main cases, because we have a pair of integers, and this is just based on their parity. So they can both be even, they can both be odd, or they can have different parities. And some of these cases have then some subcases, and one subcase then again has subcases. But this is now too technical, and I will not go into details. So altogether, we give following results. The algorithm terminates. Then we also show that the outputs of the algorithm do fulfill predefined syntactic constraints. And we show that necessary look ahead for a selection of the digits is 7. And what does this mean? This means that in order to select digit, we have in some cases to plug in 7 digits of binary expansion. Or in other words, this means that we consider our input integers modulo 128. So we don't need information about the whole integer, just modulo 128. And I have also highlighted this information from because of one more reason. And that is that our goal was to give an algorithm that selects digits after a finite number of steps. And this was for us necessary property because we show the optimality of the algorithm by building finite state machines or so-called transducer over this algorithm. So finite state machines are so Turing machines are infinite, finite state machines are finite. And we built 3 machines. The first one converts binary expansions into expansions which are computed with the algorithm. The second one weights our expansions which are computed with the algorithm. And based on this transducer, we calculate asymptotic moments for an expansion of length L. And we get the following result. The expectation is, of an expansion of length L, the expectation is approximately 0.36 L plus terms of order 1. And what does this mean? This means that our joint Hamming weight will be for pairs of integers. So if we have expansion of length L, it will be 0.36 L. So we will have 36% of non-zero columns, and the rest, 64% of the columns will be 0 columns, and we do not have to make addition. And the variance, we also have information about the variance. So this is 0.02 L plus terms of order 1. So this is now information about the average weight, but it doesn't prove the optimality. And for the optimality, we built a third transducer, which converts arbitrary inputs with digits from our digit set into expansions which are computed with our algorithm. And a transducer is a directed graph. So we label this directed graph in a way that we can run Bellman-Ford algorithm. And Bellman-Ford algorithm looks for negative cycles in a graph. And a negative cycle means for us that there exists a shorter path from start state to final state. So, and this means that there is some input arbitrary expansion which has lower weight than the one we calculate for this input with our algorithm. So that would mean a negative cycle or shorter path. And the Bellman-Ford says, luckily for us, that there is no shorter path. And this proves the optimality of the algorithm. Okay, and now how complex is this algorithm? So we compare it with existing algorithms for digits at 0 plus minus 1. So we have to pre-compute some points because we would like to use Strauss algorithm. So we have to pre-compute 12 points. If you remember, before for binary, we had to pre-compute P plus Q. So when we have our digit set, there are altogether 12 points we have to pre-compute. And for the digit set 0 plus minus 1, there are 2 points. So, okay, we need 10 points more. But then when we take a look at the average weight, then we will have 36% of non-zero columns and 50% and 64% of 0 columns. And for the digit set 0 plus minus 1, we will have only 50% of the 0 columns. So combining these 2 facts, we can see that the costs for pre-computation are offset after 71 bit. So this is worthwhile in all practical situations. And of course, if we use the same crypto system several times, then the pre-computation is required only once. And that was now the last detail I wanted to give you about the algorithm, but you can of course ask me some further questions. So thank you for your attention.